Welcome back. In this section, we're going to look at both exponential functions and logarithms for other bases other than just base e. So first things first, let's start by defining what we mean by an exponential function base a. We're putting the usual restrictions. Our base needs to be positive. Our base can't be 1. So now we can define for any real number x what a to the x would be, and that would be defined as e to the natural log of a times x. If we're thinking about this, I mean, that sort of makes sense in a sense, because if you're thinking about natural log of a times x, or in other words, x times natural log of a, that's really natural log of a to the power of x. And so really when we say e to the natural log of a times x, that's really e to the natural log of a to the x. And by what we had for our exponential and log properties of inverses, e to the natural log of a to the x is a to the x. So this doesn't feel too outlandish of a definition. What this does for us, though, is since we defined what logs were, we were able to convince ourselves that e could be defined for any real number power, which means now we can say that a to the power of can also be defined for any real number power. So the question that I said in a previous video about what do we mean by 3 to the power of square root of 2, like what does that actually mean? Well, we can rephrase it and say 3 to the power of square root of 2 is e to the power of natural log of 3 times square root of 2. And we had already convinced ourselves that e to any real number power is a fine thing to do because it's the inverse of a log, and we know logs have all real numbers as their range. So e to any real number would be fine to look at, which means now 3 to the square root of 2. That's a very valid and real number for us to be looking at. So now we've sort of patched the holes in our real number system that we were having before about wondering what actually would it mean if we were raising any old arbitrary number to a real power. So at least for positive bases, we've now got our answer. We can define things in terms of e to the power of. As far as the why we're putting some restrictions on, there's the obvious. If a was 1 for this, natural log of a is 0. Natural log of 1 is 0, which would give you e to the 0, which means your function y would just be a constant function. And we don't really consider a constant function to be an exponential function. As far as why the base, though, needs to be positive, that's also for a pretty obvious reason. Since a to the x is defined as e to this power, and a power involving natural log of a, then you know that a had better be something positive, otherwise natural log of a would not be a number. So there we go. We've got our good reason as to why does our base for an exponential function need to be positive, and that's because of our definition of things. We've defined a to the x in terms of e to the power of natural log of a times x, and so we need a natural log of a to be defined, which means we need a to be positive. If you're thinking graphically, e to the x and e to some number times x, those graphs would be the same, just one is going to be a stretched version of the other, stretched horizontally, possibly reflected in the y-axis, possibly, but it's going to look essentially the same. And so that means if we knew that the graph of e to the x was some sort of shape like this, then for any old a to the x, it'll either look like this graph stretched horizontally, or maybe compressed horizontally, or maybe reflected in the y-axis and also stretched and compressed. Any way we look at it, the graph of a to the x should be a one-to-one function, just like the graph of e to the x. We should pass the horizontal line test quite easily, which means that a to the x, for any valid base a, it should have an inverse. We're also going to see that a to the x, the way that we've defined it, it's still consistent with all of our exponent properties. So we proved earlier that e to the x times e to the y is e to the x plus y for all real numbers x and y. We're going to now show that that actually would apply for any base, that any base a, as long as it's a valid one, a to the x times a to the y would be a to the x plus y. And now we'll be able to show that this would work for any real exponents, not just nice rational ones, but any real numbers. So for example, if you had 2 to the pi multiplied by 2 to the square root of 5. Those are both irrational exponents. We'd be able to use our exponent properties and say, yep, even though those are terrible numbers, we know what we can do with them now. So we're going to prove that later on. We're going to show that all of those usual properties for exponential functions that we come to know and love, we can prove that they'll work for any real power. As far as the defining logarithms go, we're also doing them in terms of natural stuff, in this case, natural log. If I define log base a of x, my definition is it's going to be natural log of x divided by natural log of a, which you could rewrite this as a 1 over natural log of a constant, times natural log of x. This looks like the change of base formula, and in fact, it's sort of part of the change of base formula that you might remember from your pre-calculus days, the one where you could change from base A to base anything else. Usually when you used it back in pre-calculus, you were pretty much only changing things to natural logs, but your instructor would have told you that you could change to any old base you choose, as long as it's a valid base. And so later on, we will prove that log base a of x is log base b of x over log base b of a. But that's going to be something that we're going to get as a consequence of this as a definition. So this is not the change of base formula. This is not telling us we can change from base a to any other base we like. It's saying this is what log base a of x is defined as. It's this multiple of natural log of x. We're going to see that this definition for log base a of x, saying it's a multiple of natural log of x, means that log base a of x will also have the same logarithmic properties that natural log did. So we had natural log of a times b being equal to natural log of a times natural log plus natural log of b, rather. We're going to see that that property, for example, that would work for any base, not just natural log, would work for log of any valid base. And same with all the other log properties. You can prove that they'll be able to work for any base that you'd like, including the change of base formula. As far as, again, the restrictions on things, the restrictions are pretty easy to explain. If we're thinking about log base a of x being a multiple of natural log of x, being 1 over natural log of a times natural log of x, natural log of a needs to be not 0, so therefore a cannot be 1, because if that were the case, we'd be dividing by 0. Also, a can't be negative, because if it was, natural log of a would be undefined. So that's our reason for why do we have the restrictions on bases for logarithms. As we've defined things, our log base a is a constant multiple times natural log of x, and for that constant multiple to be a real number, natural log can't be 0, and it also needs to be defined, so a has to be positive and a can't be 1. As far as the graphs go, I mean, natural log and constant times natural log, that represents a vertical stretch, maybe a vertical flip if it happened to be a negative number. But any way we look at it, if we know that the graph of natural log of x is a one-to-one function, if we stretch things vertically, or even if we flip things in the x-axis, we're still going to have a one-to-one function. And so we're going to see that we wind up having an inverse for that function as well. Okay, so first let's prove our change of base theorem. And this is the theorem that allows us to change from base A to base B for our logarithms. So I'm choosing that we have the bases A and B are both positive, they're both not 1, and that the number that I'm putting in x is some positive real number. So in other words, log base A of x is something that is very much defined. I can say by definition, I know what log base b of x is, and I know what log base b of a is, because those are something that I can definitely convert things to natural logs, right? So if I'm thinking about log base a of x, I know that by definition it is natural log of x over natural log of a. If I'm thinking about the right side of the equation, this log base b of x and this log base b of a, both the numerator and the denominator, I can turn those into natural logs. The log base b of x, by definition, would be natural log of x over natural log of b. And log base b of a, by definition, would be natural log of a over natural log of b. And if we clean this up, this fraction divided by this fraction, the natural logs of b's would cancel, and we'd wind up getting natural log of x over natural log of a. And now we can see that that's the same thing, that log base a of x is defined as natural log of x over natural log of a, and this expression simplifies to give us natural log of x over natural log of a. So therefore, log base a of x should be equal to log base b of x over log base b of a. And that's true for any valid base that we feel like choosing. So as long as a and b are valid bases, and as long as whatever's going inside our original log is a positive number, then this change of base theorem will hold. So I'm not going to do all of the exponential properties and all the log properties, but as far as the ones that I'm going to show here, you're going to notice that it's actually very easy to show, and it's all going to really come back from the log properties that we saw in 5.1 or the exponential properties that we saw in 5.4. So we had this for e to the power of, for any real numbers x and y, e to the x, e to the y was e to the x plus y. So now I want to prove this with base a, any valid base. So if I'm thinking about the a to the x times a to the y, I know that I could rephrase both of those by definition as e to the natural log of a times x times e to the natural log of a times y. So that's just me using my definition of what a to the x and a to the y are. Now, previously we proved for base e that we had a log property that's, an exponential property that said e to a power times e to another power is e to the, add the two powers together. So natural log of a times x plus natural log of a times y. And you'll notice for that power, I have a natural log of a happening in both terms, so I could factor that out as e to the power of natural log of a times x plus y, which by definition, if we're thinking about how we defined our exponential function base a to the power of whatever was e to the natural log of a times whatever. So in other words, what we have here, e to the natural log of a times x plus y, that is a to the power of x plus y. So you would do a similar sort of thing if you were to try to show the one for quotients, that a to the x divided by a to the y was a to the x minus y. You would do much the same thing. Start with a's, turn them into e's, use properties of e's, and then away you go. Go back to a's. I'm going to do the same sort of thing to show that this log property that we had for natural logs also applies to log with base a. So if I started with the left side of the equation, log base a of xy, so here we've got positive real numbers x and y and a valid base a. So if that's the case, I know number one, log base a of this would be something positive. So I can say that this is natural log of xy over natural log of a by definition. And I know natural log of xy, I could use that logarithmic property and say that that's natural log of x plus natural log of y. And then I could just split things up and I could say, well, that's really just natural log of x over natural log of a plus natural log of y over natural log of a. And by definition, that is what log base a of x is. And by our definition, this is what log base a of y is. So there we go. We've shown that for the exponential functions, now we can say that this exponential property holds for any valid base and for any real powers, which is kind of great. And our log properties will work for any valid log base as well. And you could show all the other log properties kind of in the same way, and the other exponential properties much in the same way, going back into natural logs and exponential function base e. Okay, so something that we haven't confirmed yet, which is this. We've defined what a to the x was. We defined it in terms of e's. We've defined what log base a is. We've defined it in terms of natural logs. We've said that both of these functions have inverses, but we haven't convinced ourselves that they are actually inverses of each other. So f definitely has an inverse. G definitely has an inverse. The question is the inverse of f g and is the inverse of g f? Well, who can say? Well, we will be able to say very shortly once we do our proof. We start off here supposing that we've got a valid base, so it's a positive base that's not 1. And if I wanted to show two functions are inverses, I'd have to show that f composed with g is equal to x, and g composed with f is equal to x. So in other words, I need to put this log inside of this exponential function. And see what happens when I do that. Do I get just x as the result? Now, I know a lot of us are probably shouting at the screen right now saying, well, when you put log base a inside of a, they'll cancel each other out, which is what we'd like it to do, but we don't know that it does that yet. So the only thing that we know that cancels out would be e's and natural logs, because we know those are inverses of each other. So what I'm going to do is use my definition and say, well, we said log base a of x is 1 over natural log of a times natural log of x, or natural log of x over natural log of a, however you want to write that down. And that's what I'm going to put into my function a to the power of. So I'll have a to the power of natural log of x over natural log of a. Now, I remember that a to the power of, I can also write that as an exponential function. I can write that as e to the power of natural log of a times whatever the exponent is. So times natural log of x over natural log of a. And now you can see things, they're going to happen really nicely. The natural log of a's are going to cancel each other out, leaving you with e to the natural log of x. And because I already know e and natural log of x are inverses of each other, now I can say these things for sure cancel out, and now I'm feeling good about my life. It looks like f composed with g does give us just x. We still have to do the second side of things, which is to look at what happens with g composed with f. So what happens if I were to put my exponential function inside my logarithm? So g composed with f, that's my next stage. So again, same sort of thing. I'm putting my, in this case, a to the x inside of my log base a. I don't know that a and log base a will cancel each other out yet. I do know about e and natural log, so that's my next move. I'm going to rewrite a to the x as, by definition, what it is, e to the power of natural log of a times x. And that's what's going to go inside of my log base a function. So g is log base a of whatever the input is, and the input is e to the natural log of a times x. And now I'm going to use what we said for our definition for log base a, that log base a of whatever is natural log of whatever the input was, divided by natural log of a. And I'm actually almost finished here because in the numerator you have natural log of e to the power of, and I know that natural log and e are inverses of each other, so I should just be left with whatever the argument is, that natural log of a times x. So in the numerator I've got natural log of a times x, and in the denominator I've got natural log of a, and so that cleans up to give me just x at the very end of it all. So looks like after all is said and done, whether I looked at g composed with f or f composed with g, in both cases I get x. So since we have f composed with g gave us x, and g composed with f gave us x, so therefore we can say g must be the inverse of f. Or you could say that f is the inverse of g. In other words, log base a and a to the power of, that those are inverse functions. So now officially shown, yay. And that means that we now have some properties that we can now claim, because since these two functions are inverses, as long as we've got a valid base, then we know now if your base is valid, you know that y equals a to the x means x equals log base a of y. So in other words, we'll be able to solve equations by rewriting exponential things as logs or rewriting logs as exponentials. And we also now know that when we put log base a into a to the power of, or vice versa, that they'll cancel each other out. So now I'm able to solve questions like this. 3 to the power of 3x minus 1 equals 5. I know that because 5 is a positive number and 3 to the power of is always positive, then logs of those things will exist. I can certainly look at log base 3 of 3 to the 3x minus 1 and log base 3 of 5. And I know that log base 3 of 3 will cancel each other out, leaving me with 3x minus 1 on the left side of the page. And so now if I wanted to, I could solve for x pretty easily, bringing the 1 over and then dividing by 3. And there we go. I could solve any exponential equation with any base that I'd like. And similarly, if I had a log equation with any base, I could solve it as well now.